we had to complete the proof of the expression we had for the expectation of the heating time of 1, starting from 0. Okay, so let me write the result. So proposition. So if this is 0, then the expectation of the heating time of 1 starting from 0 is equal to this. So this is kind of the expression that is spitten out of the proof. But somehow you can get another expression. You just realize that this thing here, it's nothing more than 1 plus rho minus k. So if you do this, rho 0, rho minus k. Okay, I mean, nothing new here. I'm just replacing by this. When you do this, basically all the terms there, they appear 2 times because once for the 1, one for the minus k. And that's it. And you start from 0, okay, because you're just shifting the indices basically in one of the sums. Okay, so this is the result. Now let me recall what we proved last time. Okay, I won't repeat the computation, but so we did a non-rigorous computation, but in fact it gives you some rigorous implications. So we proved that if we know that this is finite, then this is equal to 1 over omega 0 plus sum from k equal 1 to n, 1 minus k rho 1 rho minus k plus 1 plus rho 0 rho minus n plus rho minus n e minus n minus 1 to minus n. Okay, so we did a computation, we ended up with that, and in the end the comment I made that yes, the only thing we used and we didn't have the right to use is this. Okay, if you want, as a consequence, you have that, well, if this is finite, this is finite. Okay? Okay, so now we need to prove that this is finite, and what we are going to do is, well, basically to do the same computation, but for a truncated version of this heating time. Okay, so so fix n, and this is meant to be large, And now I'm looking at this. And well, this thing is just, well, the probability of, well, the expectation, sorry, of the same thing, but conditioning to the fact that the first step is to the right, multiplied by the probability that the first step is to the right. Plus 1 minus omega 0, which is the probability that the first step is to the left, times the expectation condition that the first step is to the left. Okay, here nothing more than the definition of conditional expectation. Okay. Okay, so what do we do next? Well, this thing here, it's equal to 1. Okay. So let me call this 1. And this thing here, 2. So 2, well, this is equal to 1 plus. So what I want to use is the fact that, well, if I condition to this, then what I see after step 1 is a random walk in environment omega starting from -1. Okay, so okay, if you want, what I can write is E minus 1 omega. And then what this thing becomes is really 1 plus tau 1 minus 1. Okay, because the time to reach 1 for this random walk is 1 unit shorter than this one. Okay, and now this is smaller than 1 plus E minus 1 omega T0 M plus T1 minus T0 M. Okay, so here I'm doing several things at the same time, but they are really, really elementary. So I'm just saying that tau 1 is tau 1 minus tau 0 plus tau 0. I'm saying that, well, if I replace m by m, m minus 1 by m, I have an inequality. And then I'm saying that this thing is smaller than this. Okay, and finally, I have this plus this. Here I'm using the strong Markov property. This last thing, if you want, is equal to the one immediately above. Okay, the walk after tau 0 well, just belongs like a walk starting from 0. This is a strong Markov property. Okay, and this is exactly the expression we had last time, except that we had an inequality. This time we have an inequality, and we have added these things. Okay, so what we get from 1 and 2 well, is that this thing is smaller than, okay, this one here and this one there, this sum together, and you get 1. And afterwards you get 1 minus omega 0. Okay, and now what we do is we remove this term here. Sorry, remove this term here. Maybe purple is better, I don't know. And if you remove this term here, we have to add it there, and this gets us. We have to subtract it there, and this gets us this. Okay, so we get pretty much what we wanted. We get that E0 omega to 1 m is smaller than 1 plus rho 0 E minus 1 omega to 0 m. And if we iterate this, okay, we get this thing. So E0 omega. So we can apply this to with 1 replaced by 0 here and replace it there and iterate, okay? And what we get is exactly the same thing as last time. For every n. 1 over omega minus k, rho 0, rho minus k plus 1, plus rho 0, yeah, it's rho 0. I wrote rho 1, but I think it's rho 0. Rho minus n, E minus n minus 1 to minus n m. Okay, so now this is true without any assumption. Okay, let me call it. Okay, this is not the only way to go. I mean, somehow here replacing m minus 1 by m is not mandatory. You can just let things decrease by 1 every step, and then you get a sum that stops at n here. So, but in any case, yes, if you don't do this, you can just replace this by m. Okay, because you want to control every term. Okay, and now if you let n go to infinity, well, now because, well, this term is bounded, and this product here, it decreases, I mean, almost surely it decreases exponentially to 0 because of the assumption that the expectation of log rho is negative. Okay, so just the law of large number for the log of this. So rho 0, rho minus n decrease to 0. So what we get is that this is smaller than 1 over omega 0 plus the sum from k equal 1 to infinity, 1 over omega minus k rho 0 rho minus k plus 1. Okay, the right-hand side does not depend on m, so because this is valid for every m, we can use, I don't know, monotone convergence or dominated convergence, whatever you want. And this is also true here. And okay, by here, using the fact that this decreases exponentially and that this is bounded, you know that this thing is finite. So far, so good. Okay, so we proved the finiteness of the expectation of tau1, and we proved one of the two bounds we wanted. Okay, so we need to prove the other bound. But the other bound, it's good we have it from there. So, okay, the other bound. Well, you can just don't look at this term. You have that this is true for every n. So this is true when n goes to infinity. Okay. So this ends the proof of the law of large numbers. So I mean, if you remember, this was one part, and the other part was to show that well, if on top of this the expectation of rho was strictly smaller than 1, then the expectation of this with respect to omega was finite, and together with the ergodic theorem, we could prove an average law of large number, okay, which is the same as an almost sure quenched law of large number. Okay, so now I guess several questions come to mind. So, well, if we have a law of large number, can we go further? And can we prove central limit theorems? So that's a natural question. And perhaps the other question, and more intriguing, is the one, okay, what happens when we have zero velocity and transients to the right? And somehow these two questions are related. So today we are going to focus on the central limit theorem, but I'm going to do a bit of digression, proving something also for the case where you're any question about this proof? Okay. Okay, so yeah, let's start. Okay, we are going to discuss the CLT, and now let's see what we mean by CLT. Because like for almost sure convergence, it's kind of clear that average and quench convergence are the same. But when we talk about central limit theorem, we have a convergence in distributions, so things get a bit different. Okay, so let me make this comment about CLT. So what are we going to do? Well, what we have seen is that, okay, we want to prove a CLT, okay, for the walk, but the quantity to which we have, well, which is nicer to treat are these reaching time. Okay, because, well, if you consider them in a quench way, there are some, I mean, the increments are independent. And if you consider them in an average way, the increments are ergodic. So, so this is what we are going to see to do. So natural thing to do is prove something for OK, and then convert, perhaps no brackets here, convert this result into something about xn. Okay, and basically we want to take advantages of two things. Okay, either that tau k is an ergodic sum, under E0, and this would be to prove an averaged CLT, and for this, what one would require is really, well, a notion of CLT that requires that relies on ergodicity. Okay, and well, such things exist, and of course you need more than ergodicity because central limit theorem is somehow something quantitative, and ergodicity just gives you decorrelation, but not with any rate of decorrelation. Okay, so this is one option. The other thing is that tau k is a sum of independent random variables. So this is quenched. And well, here to get a CLT, what would need a version of the central limit theorem that only relies on independence and not on the fact that the variables are IID. And in fact, it's not super difficult here to find out what's the optimal condition you need on the distribution of the variables to have such a CLT. So we are going to see this. This is called the Lindeberg-Feller condition. Okay, and this gives you the Lindeberg-Feller CLT, which tells you, well, if you have a sum of independent variables that satisfies this, this, and this, then you have a CLT around the mean. Okay, this is easier than that, I would say. And also, I have not studied that yet, so we will start with this today. Okay. Okay, so what's the result that one would like to prove? Well, well, something like that, okay? Or what? perhaps. I mean, you might have some uncertainty about what you might find here, but that would be the objective. And here you can already remark something is that, well, you're recentering by the mean, okay? And the mean itself is random. Okay, so this kind of basically indicates what the next step would be. Okay, so here I would put a sigma 1 here. Okay, this kind of tells you what the next step would be to prove an average CLT. So if you look at the average CLT, what you want to do is to recenter by the average mean. Okay, and you can decompose this thing into two terms. This thing and this thing. Okay, so now, if this thing is right, okay, and if the variance here does not depend on omega, but okay, I'm going to spoil you a little bit. This is not going to depend on omega. Well, then somehow this converges to a Gaussian which is independent of omega in distribution. Okay, so I mean, these two things they are not independent for fixed k. Okay, but when I mean, this theorem tells you that asymptotically they become independent. Okay, so asymptotically this does not depend on omega. Okay, and this is a function of omega. So, and here is a plus, I guess. So here you will use, well, this converges to n0 sigma 1 square in distribution. And this, well, if we have some ergodic central limit theorem, well, somehow the increments of this are an ergodic sequence. Okay? And they are an ergodic sequence actually in a for a measured dynamical system, which is actually much simpler than the one we had before. Okay, because now you just need to consider omega with the shift. Okay, so this will be much more convenient. Okay. Okay, so if you prove a CLT for this and for this, because the two things are independent, basically, you get for free. I mean, of course, at the time when we'll do a rigorous proof of that, but the sum should converge to this. Okay, so basically, in the average CLT, you have two sources of variance, and in the end, they sum up. So yeah, the two CLT we are going to prove is, well, one where you recenter by something random, and you converge to a Gaussian with a smaller variance, and one where you recenter by something deterministic, and you get additional fluctuations, basically, that comes from the fluctuations of this term. Okay. So, yeah, what's, well, the minimal technical condition we must have to prove CLT? Anyone would have a guess? The basic requirement that one must have, if not, I mean, it's not that the CLT cannot hold, but our tools won't be able to prove it. We need finite second moment. So, minimum requirement. Okay, and so okay, we have a simple characterization for, sorry? Sorry? So what should be the condition on rho on the environment omega such that this is true? Oh, yes.
Yeah,
okay, just think about what we had for the condition for finite expectation. So what should we have here? Expectation of something should be finite. What thing? Okay, so we are going to prove this. In fact, we are going to prove a little bit more. So because I think this is going to help to understand things later on. So yes. Okay, so we are going to prove that you have an average moment of order gamma if and only if rho 0 has a moment of order gamma for every gamma. Okay, we are not, okay, no. What I'm claiming is that this is true, and we are going to prove slightly less, but I think after what we are going to prove, you are going to be quite convinced that this is true. Okay, and there is one tool, okay, when you want to deal with, so this is something which is quite relevant when you want to do is this problem of statistical mechanics with disorder. Sometimes you don't have integer moments and you have to deal with these things. And when you want to compute the moment of order 2 or 3, whatever, well, you have a square, you can expand it. And then you have some independent terms, and you can. So in general, for these kind of things, you can hope to get exact expression. But as soon as gamma is not an integer, you cannot. But there are a few tricks. Okay, so you have to deal with inequalities, and there are a few tricks you can use. So one of them is Jensen's inequality. And there is another one, which I think is not a consequence of Jensen, but perhaps it's just that I never found out how you get it from Jensen. But it's the following. So, and we are going to use it repeatedly. So if AK is a non-negative sequence, somehow I'm taking this with countable sums. It's also true for uncountable sums, just immediately. So what you have is that if gamma is larger than 1, okay. Let's do it for gamma smaller than 1 first. So if gamma smaller than 1, okay, let's do it with theta. If theta is smaller than 1, then the sum of the AK to the power theta is smaller than the sum of the AK to the power theta. And if theta is larger than 1, things go the other way around. Okay, so this is not very difficult, but if you've never seen it, you might wonder how you prove that. So I'm just going to do it. Okay, one first thing is that for 2, okay, is just 1 for 1 over theta. And A prime k is equal to AK to the 1 over theta. Okay, if I want this inequality, it's the same as proving that this is larger than this sum to the 1 over theta. Okay. Okay. What I have is that for theta prime. Okay, what I have is that sum of A prime k theta prime is smaller than sum of A prime k to the theta prime. Okay, and this is exactly what we want. Okay, you take this to the power theta. Okay, and you get, well, this is AK, this is 1, and this is AK to the power theta. Okay, so we just need to prove one of them. Okay, so now the idea is that you just need to prove that if you prove this, you'll be good. Okay? Why? Because if this is true, then if you look at this, well, this is equal to A plus B plus C to the power theta. This is smaller than A to the theta plus B plus C to the power theta, which is smaller than A to the power theta plus B to the power theta plus C to the power theta. So if you have it for two terms, you have it for finitely many terms just by iterating. And if you have it for finitely many terms, you can get it for infinitely many terms just by taking limits. Okay, I mean, both sides are the increasing limits of what you have with finitely many terms. Okay, and now this case here, well, you can just divide by A on both sides. So you just really need to prove that 1 plus S to the theta is smaller than 1 plus S to the theta. Okay, so you have two functions. They coincide at S equals 0. So we are just going to make a comparison between the derivatives, and we are going to be good. Okay, so okay, derivative of the left-hand side is just theta 1 plus S to the theta minus 1, and of the right-hand side, it's theta S to the theta minus 1. So, yeah, theta is smaller than 1, so this is larger than this, and we're done. Is the proof okay? Okay, so now I want to prove part of this. Okay, so we are going to prove two things. Basically, we are going to prove two implications. It's just that the two implications will be for different ranges of theta. So in the end, we will have this for theta between 1 and 2. But I think the proof will convince you that this is also true outside of theta equal 1. Gamma between 1 and 2. But I think the proof will convince you that this is true everywhere. So lemma 1. I want to prove that if gamma is larger than 1, then yeah, I think this is okay, so we are going to prove this. Okay, so in fact, we are going to prove the contraposition of this statement. So we are going to prove that if this is infinite, then this has to be infinite. Okay, so okay, so first thing, we are going to bound this by something for which we know the expression. And here, somehow, the assumption will be a good indicator of what we should put here. So any idea of what we can do here? Okay, let's this is equal. So what can we do? Yeah, but this is a bit annoying because then when you will have to 1 plus 1 to the gamma, I think this is probably what you have to do if you want to do it for gamma smaller than 1. But here, let's be simple and use the fact that gamma is larger than 1. So what we can do is simply put this gamma outside of the expectation because we know we have an expression for the expectation of tau 1. So we are just using Jensen. Okay, and okay, now we will try to figure out what to do here. So okay, so let me rewrite. Okay, I will use the other expression for. So this thing is, we said, 1 plus 2 times the sum from k equals 0 to infinity, rho 0, rho minus k. Okay, so okay, so let's forget about perhaps the 1 and the 2. We don't really care. And let's put an n here. Okay, so I think what you can do is pretty much obvious when gamma is strictly okay. Of course, you spotted something. Yeah. Okay. This was there. So this is because of course we are still working with our uniform ellipticity conditions. So all these rho zeros, they are finite moments. Okay. So now, if you want a diverging lower bound here. Okay, yeah, everything is getting wrong. So after this proof, we are taking a break. For me too. Okay, and here we are going to assume, okay, we are proving the contraposition, so we are going to assume that this thing is larger or equal to 1, okay, and shows that this thing is infinite. Okay, so if this thing is strictly larger than 1, you just need to keep one term. Okay, if this thing is equal to 1, somehow one term is not enough, so you need to be to do something more. So we are going to use Jensen, okay? So to the gamma. Well, it's larger. Okay, let's stop at n minus 1 to n terms to the sum from k equals 0 to n minus 1, rho 0, rho minus k, to the gamma. Okay, by Jensen now, So this thing, I can write it as a mean. Okay, this is just 1 over n, and I just have to multiply by n to the gamma here. And this is larger by Jensen than n to the gamma minus 1 sum k equals 0 to n minus 1. Rho 0 to the gamma, rho minus k to the gamma. Okay, are things going in the right direction? Yes. Or are they? No, I see. Okay. I think that okay. Perhaps you can confirm me. I'm using Jensen in the wrong direction, I guess. Okay. So wait. Okay, so let's, okay. If gamma is equal to 2, this works, okay? If gamma is not equal to 2, okay, if gamma is not an, if gamma is an integer somehow, you don't need to worry about this, and you have that this is larger than this, okay, you're just keeping just diagonal terms. Okay? Yes, it's a lemma. But in my notes, it's Jensen. You know, but the lemma is not Jensen, so it's a lemma. Yes. Perfect. So we have what we want. This is good. Then this is okay. And this is larger than n. So this goes to infinity. Thank you. Okay, so let's take a small break, and I come back with the other lemma. So this is for the case, yes, gamma larger than 1, and yes, I would say probably you can treat the case gamma between 0 and 1 with a reasoning along this line, but okay, here basically you need to do something else. You can try to use this recursion, and the important thing is that at some point, okay, you should make these terms appear. These products of rows. Okay, somehow, I think at some point we will prove this, but indirectly at least, and using some other reasoning based on the potential created by the environment. Okay, and yes, now let me prove the complement. Well, basically the implication in the other direction, and okay, this is going to take some time. So. Let me erase this, and next time I have to use it, I will remember it better. So what's lemma 2? Lemma 2 is, well, for all gamma in 0, 2, and well, it will be quite clear why we have this restriction. 2 included. 2 included is important because we want to prove the proposition. And yes, so it's the other implication. So it's how should I write it? Yes. Rho 0 gamma finite smaller than 1 implies that E 0 to 1 to the gamma is finite. Okay, so what I'm going to do is to give you a proof in the case where gamma is smaller than 1, because it's, well, it's almost immediate. And then it will kind of give us what's required to prove the case gamma smaller than 2. Okay? But before doing this, basically, the case gamma smaller than 1 is interesting because it already tells you something about the random walk when this condition is not satisfied. No, okay. It already tells you something about the random walk. Yeah, okay, it already tells you something about this case. E rho 0 small, larger or equal to 1 E log rho 0 negative. Okay, so this is the reason why this lemma. Okay, this lemma, of course, this proposition will be applied to prove the central limit theorem, but somehow this will have other consequences. Okay, so let's see how the proof works for gamma smaller than 1. Well, here we can use directly the lemma because we have this thing here. Okay, so this is smaller than the expectation of, well, 1 plus 2 to the gamma times the sum from k equals 0 to infinity rho 0 rho minus k to the gamma. Okay. Okay, here I'm just using the lemma to bound. Okay, this is an upper bound for the expectation of tau 1. Sorry, what am I doing here? Ah, yes. Okay, and here I'm using Jensen here. Okay, first I'm using Jensen. And here I'm using the technical lemma. Okay, sum of ak to the theta is smaller than sum of ak to the theta. Okay, and then this thing is equal to 1 plus 2 to the gamma times the sum from times 1 over 1 minus the expectation of rho 0 to the gamma. Yes, okay. It's a geometric sum, but the first term is to the power 1. So. Okay, so this in particular is fine. Okay, so now let's make this. Okay, so first two observations. So yeah, here we are using twice the fact that gamma is smaller than 1. Okay, just to use this Jensen and to use the lemma. So, well, if gamma is smaller than 2, then the good news is that gamma over 2 is smaller than 1. So what we are going to do, what we kind of we are required to do in the case gamma between 1 and 2, okay, and then this is basically what is required here. Well, we need an expression for the quenched second moment of tau 1. Okay, and this seems doable. Like if we reproduce what we've done for the first moment, okay, perhaps we can get something for the second moment. So the expression will be a bit messier, but hopefully what will pop up in the expression will be second powers of the row i's, and then when you get them to the power gamma over 2, things will be all right, and things will be summable afterwards. So this is our hope. But before doing this, let's try to exploit this result. Let me give you a proposition. And it will be the following. So So let's reuse the notation x star n. It's the maximum over m smaller than n of xn. Okay, so it's the largest. What we are going to show here is that if you have if the first moment of rho is finite, you know that you go ballistically. So if you have an information of this kind, somehow it will give you a lower bound on how you diverge to infinity. Okay, but which has to be smaller than ballistic. And what you get is really well, that the limit when n goes to infinity of xn star over n is equal to infinity. Okay, xn star over n to the gamma. Okay, the reason you have xn star and not xn is, well, it's technical and somehow showing that if xn star diverge, this is also true for xn. Okay, so okay, we are going to prove this, but what? Ok, tá. Dá para ver?
Não.
Ah, então, vocês têm perguntas? Não. Então a gente vai descansar. Não, então, bom, isso vai dar a intuição que é mais ou menos esse exponente aqui, tá? Então, bom, eu posso fazer. Mas não vai dar para ver, né? Matemática sem quadro é difícil. Matemática com quadro é difícil, então... Sim.
Você só usou só que a média do XP0 é menor.
Sim. Yeah, so basically we are trying to prove this. It's just that one implication we prove it for gamma larger than 1, and the other we prove it for gamma smaller than 2. So in the end, what we are doing is that you're proving this for gamma between 1 and 2. Somehow, okay, for gamma larger than 2, yeah, what I told you for gamma smaller than 2, it's true for gamma smaller than k. You can get an expression for the quenched case moment of tau 1, okay, and then gamma over k is smaller than 1, and you can. So what we will do for the second moment, what we will do for gamma smaller than 2, you can repeat it for gamma smaller than k. Okay, just the other lemma for gamma smaller than 1, you really need some extra input. For this, I guess, this one here. Okay, for gamma between 0 and 1, you need something. Okay, but somehow this is just the part that I'm not going to use, so this is fine.
Seeing that we have a bit of time, could you maybe give, well, a few classes ago you were talking about the omegas and their distribution. You said let's bound them away from 0 and 1.
Yes.
And maybe could you just give out the ideas on how do you extend to like non-bounded omegas? Or does it make much difference?
No, it doesn't make any difference. It's just that you have these if omega is not bounded, then maybe these things are not defined, and you have to be careful. Somehow, yeah. So if basically, yes. So, for instance, when you look at this thing with the expectation of log rho, yeah, if this thing is infinite or equal to minus infinity, everything is okay. If this thing is not defined, then you might run into some trouble. So yes, really, it's really something case by case. You cannot have something fully general, but yeah, I mean, there's yeah, generally, I mean, in the end, it boils down to this kind of stuff. Like you need some integrability condition of omega close to 0 or close to 1. And these things kind of imply these integrability conditions. So,
does anything weird happen whenever if you could take some omega that doesn't satisfy anything like that? Do you know anything weird? Just that we can't quantify it using.
No, so for instance, what you can have, okay, but it's not crazy things. So for instance, okay, here what I was going to tell you is that this is actually, there is some light here, right? Okay, so.
It's the inflection part.
Sorry?
I think that's the worst part.
This is the worst part? Okay.
Yeah.
So, what's the best part?
I think, yeah, the middle to the right is better because the reflection is so light.
This one here?
Yeah.
Okay.
Se eu ligo um projetor, coloco uma tela branca, eu acho que vai dar certo. Ligar o projetor e colocar uma tela branca aqui.
É porque, o projetor está no...
Tá no break. No meu equipamento ali, o projetor está no break. Aqui também está no break. Vê se dá certo. Botar uma tela branca. Clarear aquela parte ali.
É um senso da superioridade.
Deixar que vai ficar mais forte. Dá pra usar aquela parte ali.
Que lindo. É a matemática survivalista. Vamos lá. Então. A gente pode olhar numa coisa aqui que vai ser... aqui vou botar o quê? Aqui vou botar gama. E aqui vou botar a esperança de ρ 0 elevado a gama. E eu vou pegar duas hipóteses antes de fazer o meu desenho. A primeira vai ser que log ρ0 tem esperança negativa. Tá? Porque é o que interessa a gente. A segunda coisa que eu vou querer é a seguinte. Eu quero que a probabilidade que ômega 0 estritamente menor que 1/2 é positiva. Tá, então, essa segunda coisa é só para não ter um caso completamente trivial. Tá? Então, e se eu olho aqui, então, para γ igual a 0, aqui vou ter 1. Tá? Essa hipótese aqui está me falando que a derivada aqui é negativa. Tá? Porque a derivada disso deve ser exatamente isso, ou uma coisa. Tá? Essa hipótese aqui me fala que ρ0 é maior que 1 com probabilidade positiva. Tá? Porque ρ é 1 menos ômega dividido por ômega. Então, se isso é menor que 1/2. Tá? Então, o fato que isso vale quer dizer que quando γ vai para infinito, isso cresce exponencialmente. Tá? Então, bom, eu vou para infinito aqui. E acho que essa coisa é a esperança de uma função que é convexa em γ, então é convexa. Então, tem um γ estrelinha aqui, que é tal que a esperança de ρ0 γ estrelinha igual. Tem um único assim. Tá? Então, o que a gente viu até agora é que se γ estrelinha é estritamente maior que 1, tá? Isso quer dizer que γ estrelinha, peraí. Sim. Γ estrelinha é estritamente maior que 1, implica, I have to speak English, law of large number. So if gamma star is strictly larger than 1, then you have a law of large number. Okay, because what we are proving now is gamma star is strictly larger than 2, then you have a central limit theorem. Okay? And now what's happening now, what we are starting to prove here, okay, is that if gamma star is between 0 and 1, well, you already know that you have velocity 0, but what turns out is that vai cair tudo. Mas tá. Mas depois vai acontecer algo? Vai voltar um dia?
Acho que vai acabar o projetor e a gravação.
Só vou parar de gravar a aula, tá?
Tá. Então, neste caso, vai ser, o xn vai se comportar com n, a potência γ estrelinha, que é uma potência menor que 1. Tá? Então, isso aqui estamos mostrando uma cota, tá? Bom, de um jeito um pouco fraco, porque tem uma estrelinha aqui, mas isso não é muito importante. Tá? Mas com a hipótese que temos, o que estamos fazendo mais ou menos é botando um ozinho de 1 no exponente. Tá? Bom. E, bom, a gente pode também se fazer a pergunta, o que acontece quando gama estrelinha fica entre 1 e 2, tá? E neste caso, o que vamos ter é que, bom, sabemos que tem uma lei dos grandes números, yeah, on the other side, we don't have a central limit theorem. It's not expected that we have a central limit theorem. So what's going to happen is actually that this time xn minus its expectation divided by n to the gamma star, this thing is going to converge to something. Okay, so yeah, you might wonder why this is the case. And
shouldn't it be 1 over gamma star?
No, it's gamma star because you get 1 over gamma star. Okay.
Because when it's 2, you do tend to get the central limit.
Yes, you're right. So yeah, why is it 1 over gamma star and not gamma star? So why does it change from here to there? Because all these results, you get them for tau. Okay? Here, when you invert the result, you invert the exponent. But here, somehow, because you have the law of large number and this fluctuation around the mean, you get the same fluctuations for tau and for x. Okay? So, yeah, so where do these results come from? These come from result about tau. Okay? So, like, tau k behaves like k to the power 1 over gamma star. And, okay, I'm not going to prove this fully in this course, but what we can do instead is to prove this result from some of IID random variables for which you know for which the tail distribution is decaying like t to the minus gamma. Okay, so if you look at the distribution of tau1 under, if you look at the probability that tau1 is larger than t, okay, this thing roughly behaves like t to the minus gamma. Okay, actually, under mild conditions, this really is asymptotically equivalent to a constant times t to the minus gamma. And if you have IID random variable satisfying this, then these statements are not too difficult to prove. So yeah, I think perhaps what I should do in this class is try to prove you this and then prove things for IID random variables. And then take the argument that, well, these things are not very different from IIDs. There are correlations, okay? The sequence is only ergodic, but these correlations, they decay kind of fast, okay? Okay, and I think, I mean, this is, perhaps we shouldn't do math during the five last minutes of electricity we have. So, okay, perhaps I will end here, and we will take things back tomorrow if lights come back. Okay.